All right, this is Unit 6, Section 12 of AP BC Calculus only. So again, this is BC only. We're doing integration by partial fractions. If you're an AB student, please skip to Section 14 of this unit. So skip to Unit 6, Section 14. If you're in AB, for BC folks, stay here. So what we're going to be talking about today is using partial fractions decomposition, which is a skill that you learned with me in pre-calculus, to find the integral of rational functions that you can't integrate otherwise. So let's go ahead and review the skill we learned in pre-calc. So partial fractions decomposition is essentially the process of taking a single rational function, right, a single fraction, and splitting it up into multiple fractions that are easier to integrate. So in order to do that, the first note is that if a fraction is improper, meaning the numerator degree is greater than or equal to the denominator degree, you're going to have to divide first before doing all the steps that we see below. We'll deal with that later in an example. So partial fractions decomposition setup. The first thing we're going to do is fully factor a denominator, right? The second thing we're going to do is we're going to give each factor its own fraction using some guidelines. So here are the guidelines below, these guidelines right here. Linear factors get a constant numerator. So for instance, if I had a denominator that factored into x plus 1 and x plus 2, and let's just say x squared plus 3 to make a point, right? Let's say I had something that looked like this. I would have a linear term, a linear factor rather for x plus 1, so it would get a constant numerator. I have a linear factor for x plus 2, so it would also get a constant numerator. But then x squared plus 3 is a quadratic factor, so it would get a linear numerator, which would be cx plus d. So that's what we mean by linear factors get constant numerators, c, a, and b. Quadratic factors get linear numerators. You're not going to have any cubic factors, but for the record, if you had a cubic factor, it would get a quadratic numerator. And lastly, repeat factors get one fraction for every power up to their max. Now, what we mean by that is, let's say I had a denominator that looked like an x plus 2 to the third. When I split it up, there'd be a fraction for the x plus 2. There'd be a fraction for the x plus 2 quantity squared. And there'd be a fraction for the x plus 2 quantity cubed for every power up to the max. Since the x plus 2 itself would be a linear factor, these are all just going to have a constant numerator, but that's what we mean by repeat factors. In order to find the constants, I'm going to get a common denominator on both sides of my equation that is identical to the original denominator. We'll deal with that in a bunch of examples. And then I'm going to use clever substitution and a bunch of other methods to find the numerical values of a, b, c, and all these other things. In APBC, which is right now, we're going to use partial fractions decomposition to split apart these rational functions, and then we're going to use our calc skills to integrate. So let's go ahead and walk through this. So the first hint that this is a partial fractions problem is that the denominator factors. So your brain should always do a quick double check that it's not u sub. So your brain should always think, is it u sub? Because even though you're in BC now, u sub is still the most common method of integration. So you should just double check and you say, wait a second, du would be a 2x minus 1, which is not, this thing is clearly not this thing. So nope, it's not u sub, right? So you don't have to write that down. I just want to point out that your brain should always do a quick double check that it's not u sub. So it is not u sub. Congratulations. Once you see that, given that the denominator factors, it's likely partial fractions decomposition. So I'm going to go ahead and do my partial fractions decomposition on the negative 5x plus 4 on top of, when I factor, I get an x times an x minus 1. Since both of these are linear factors, I'm going to get a constant over the x plus a constant over the x minus 1. So this is my setup, right? So when I described the setup in the previous slide, this is the setup. I'm then going to get a common denominator that is the x times the x minus 1 on both sides. So when I do that, what's going to happen is essentially the a is just going to get multiplied by whatever factor his denominator is missing, which is the x minus 1. The b is going to get multiplied by whatever factor his denominator is missing, and I'm going to have this nice same common denominator. See how those are the same. So I can cheat and just look at the numerator, right? So if the denominators are the same, then the numerators also have to be the same. So then once I'm here, I'm going to do a thing that I call clever substitution, right? I notice that this statement has to be true for any x. So I'm just going to pick some easy x's. I could pick any x I want. I could pick 8 million. I could pick 1.2875. It would just be a weird choice. So I'm intentionally going to pick the easy x's. I'm going to pick x as 1 because that would knock out this entire a term, and I'm going to pick x as 0 at separate turns so that I can find each of these variables. So when I pick x as 1, I get a negative 5 plus 4 on the left-hand side. On the right-hand side, the a term gets knocked out, and I get a b times 1. So I seem to get that negative 1 is b. Great. When I plug in x is 0, on the left-hand side I just get a 4, and on the right-hand side I get an a times a negative 1 because the b term got knocked out, so I get a negative 4 as my a. So what I now know is that this partial fractions decomposition is a negative 4 over x plus a negative 1 over x minus 1. Well, when I go ahead and clean this up, that's essentially two integrals that I should be able to do pretty easily. Now the second fraction is technically u sub, but because your u is your du would also be dx, it's going to integrate pretty easily into just a natural log. And that's my answer. Now you could see that the AP puts these together using log properties, but that's the gist of how it works, right? So that's my answer, and that's been integrated. If the AP put it together as log properties, it would be slightly more complicated. It's not awful. Put together, it would probably look something like this. Both the x minus 1 and the x to the fourth would go on the bottom because of those negatives out in front, and it would look something like this. And that's the gist. So that's also an okay answer, and there are other equivalent answers using log properties. But that's the idea. So notice I have to do all this partial fractions decomposition that actually has nothing at all to do with the calculus part. The integration part's usually pretty straightforward, and it's quite often a natural log. All right, so let's go ahead and walk through another one. So again, you should always do a quick check and say, if u were the denominator, is this u substitution, right? If that were true, your du would be a 2x plus 9 dx, which is clearly not this. So again, this doesn't have to be a thing that you write down. It should just be a thing that your brain thinks about, because realistically, it's a common trick that every once in a while they give you something that's u sub. So partial fractions decomposition of 3x plus 10 over an x plus 4 times an x plus 5. I'm not going to go into how you factor that because at this stage of the game we kind of just need to know how to factor. They are both linear factors, so they both get a constant numerator. When I get my common denominator, and you can kind of cheat here if you're able to skip a step, the a is going to be missing the x plus 5 to get the common denominator. The b is going to be missing the x plus 4 to get the common denominator. So these are just my numerators all over this common denominator of x plus 4 times x plus 5. My clever substitution, I should pick x is negative 5, because that'll knock out the a term. So I'm going to get a negative 15 plus 10 equals nothing where the a was, and then a b times a negative 1. So I seem to get negative 5 is negative b, which means b is 5. When I plug in x is negative 4, I'm going to get negative 12 plus 10 equals a times a 1 plus nothing. So I seem to get negative 2 as my a. So again, that part's not actually calculus, right? So what that's allowed me to do is essentially split this up into two natural log integrals. So I get a negative 2 over an x plus 4 and a 5 over the x plus 5. And technically, again, both of these are u sub, right? Because your u would be the x plus 4, but since du is just equal to dx, I don't really have to worry too much about it when I integrate. So I'm going to get negative 2 times the natural log of the absolute value of x plus 4, plus a 5 times the natural log of the absolute value of x plus 5 plus a c. And that answer is totally right. But again, the other way you might see that answer is you might see it combined as a single logarithm with the x plus 5 all to the fifth, the x plus 4 to the second on the bottom. So the other way you might see this is something like this: x plus 5 to the fifth over an x plus 4 to the second. It's on the bottom because of the negative 2. And that's also a possibility. I don't really care which way you write it. If it were me, I would write it this way on a free response, but just be aware that if something is multiple choice, you could be expected to use log properties to manipulate your answer. All right, so again, you can do the quick double check. If your u was x squared plus 6x plus 9, right? So if that were your u, and I'm just suggesting you do this because you never know, sometimes it really is simple u sub. You're going to get a 2x plus 6, which is clearly not a 7x minus 15, so you can go ahead and cross that off. When I factor the denominator, I get a repeat factor. right? That's an x plus 3 times an x plus 3. So when I do my partial fractions decomposition, I have this negative 7x minus 15 over a repeat linear factor. What that means is that each time that factor occurs from the first time up until whatever the higher degree is, I'm going to make one fraction. So in this case, I have an x plus 3 over an a and an x plus 3 quantity squared over a b. It's the first power and the second power because it goes all the way up to the second power. Both of the numerators are constants because although this is an x plus 3 quantity squared, the factor itself is still linear. So when I get my common denominator, and this is a pretty common mistake, the b isn't missing anything, right? So this thing's not missing a factor, right? The common denominator I want to get is an x plus 3 quantity squared, and I already have an x plus 3 quantity squared. So the a, right, the a term is missing one of the x plus 3's. The b term isn't missing anything. So I'm going to use clever substitution. I pick x is negative 3 because that'll knock out the a term. I get 21 minus 15 equals nothing plus b, so I get 6 is my b. Now that I know b, it literally doesn't matter. I'm just going to pick the easiest x that I haven't chosen yet, which is 0. It's not going to knock anything out, but I already know b, so it doesn't need to. I'm going to get a negative 15 equals a times 3 plus 6. So I get a negative 21 is 3a. I get a is a negative 7. So now I know a and I know b. So a is a negative 7 over an x plus 3. And b is a 6 over an x plus 3 quantity squared. Now, again, technically both of these are u sub, but because your du is dx, it's a little more straightforward. If you need to see this as u sub, right, if you need to physically write these as u sub, you can, that's fine. This one's going to be a natural log, right, because this one behaves as a negative 7 over u du, that's a natural log, but this one won't be a natural log because this is a 6 u to the negative second du, right? If we were playing this game, that's the way that would work. So what's going to happen is I get that this integrates to a negative 7 natural log of the absolute value of x plus 3. And then when I up the power by 1, this becomes a negative 1. So I get 6 u to the sorry, it's not a u because I didn't actually do u sub. I just was showing you. It is technically u sub, but most of us don't write it. So negative 6 u to the, and I just did it again, people. All right. Negative 6, the thing I would call u to the negative first plus c. The reason it's negative 6, I was going to write it as a plus 6 and then divide by negative 1, but the reason it's negative is because I up the power to negative 1 and then divide by negative 1, which is why it's a negative 6. You'd probably be more likely to see this as a negative 7 natural log of the absolute value of x plus 3 minus a 6 over an x plus 3 plus that c. I kind of ran out of space, but you get the idea. All right, so go ahead and try a P3. Again, you've kind of got the gist at this point, I think, that if I have the denominator as my u, the top is not du. I just wanted to throw out that that is technically an option sometimes, but here it's not going to happen, and you can see that. If my denominator were u, my du would be a 2x minus 4, which is definitely not a negative 3x plus 11. So I'm going to go ahead and do my partial fractions decomposition. Right, so I'm going to get that this negative 3x plus 11 over an x minus 2 quantity squared is an a over the x minus 2 plus a b over the x minus 2 quantity squared. Again, this is the common denominator I want, so the b is already good. It's already over that denominator. So I'm going to get negative 3x plus 11 equals a times this x minus 2, because that's the factor that this fraction would be missing, plus b. When I do my clever substitution, I pick x is 2 to knock out the a term. So I get negative 6 plus 11 equals nothing for a plus b. So I get 5 as my b. Now I pick the easiest x I can think of, which is generally going to be either 0 or 1. I think 0 is the easiest. So I'm going to get 11 equals a times negative 2 plus 5. When I subtract the 5 over, I get 6 equals a times negative 2. So I get a as a negative 3. So now I have a and b. So then I can go ahead up here, right? So this part isn't actually calculus. It's just a part that you need to do the calculus. I'm going to get that this is the integral of negative 3 over this x minus 2 plus a 5 over this x minus 2 quantity squared with respect to x. Again, if you need to do this as u sub, you can say that this is actually negative 3 over u du because du would just be dx in this situation, right? And the same thing with this thing. If you need to see it, this is a 5 with a u to the negative second du, right? If you need to see it, again, because du is just dx. So I end up getting that this is a negative 3 natural log of the absolute value of x minus 2, right? And then this is going to be minus of 5, x minus 2 to the negative first plus c, and that answer's fine, absolutely fine, but it's more likely that you'll see this with the x minus 2 to the negative first written as an x minus 2 in the denominator. Either is totally fine. So that's slightly more likely, but that's the idea. All right, so this one is improper, okay? So this is an improper fraction. I need to divide first, sorry. As an improper fraction. What that means is we need to divide first. So there is a caveat to the synthetic division thing. There is a way to do synthetic here, but it's not pretty. If you have a nonlinear divisor, this is an x squared minus 6x plus 5, it's really not worth it to do synthetic division. It is possible. When I was in high school, I had a high school teacher in pre-calculus tell me it was not possible, and I was pretty sure she was wrong, so I spent a good amount of time figuring out why her statement was incorrect. And what the statement she said should have been was, it's not worth it to use the synthetic division shortcut because it's not a shortcut anymore, but it was possible. All right, so to make x squared look like a negative 2x squared, I multiply by negative 2, right? So when I do that, I'm going to get a negative 2x squared plus a 12x minus a 10, and then subtract straight down. The negative 2x squared minus a negative 2x squared is gone, which is the whole point of the division, right? The 4x minus the 12x is a negative 8x. And the 14 minus a negative 10 would be plus 10, so that's going to be a 24, right? So at this point, this is my remainder, right? This is my remainder. And what I get is that this integral is actually a negative 2 plus this negative 8x plus 24 over the original divisor. So the trick here is that this piece is just going to integrate to a negative 2x. That's easy enough. Like, this is fine, right? This piece I would just integrate. But this piece is going to require partial fractions decomposition. So let's go ahead and keep doing that bit right there, okay? So when I go ahead and do the partial fractions decomp, and this is obviously a longer problem because now we're just starting the stuff that was the entire meat of the last problems. So this was a negative 8x plus 24 over. When I factor this, this is an x minus 1 and an x minus 5. And you can see how important it is to be able to factor because it's such a minor step in a much larger problem. So I get an a over the x minus 1 and a b over the x minus 5. So we've seen this several times now. When I get my common denominator, what's going to happen is the a gets multiplied by the factor it's missing, the b gets multiplied by the factor it's missing, and the common denominator would all end up being an x minus 1, x minus 5 on both sides, which means I can ignore it. When I do my clever substitution, I'm going to start with 1. That's going to give me a negative 8 plus 24 on the left-hand side, and an a times a negative 4 on the right because the b gets knocked out. So I get 16 equals negative 4a. So I get that a is a negative 4. All right. Next, I'm going to plug in x is 5. And when I do that, I'm going to get negative 40 plus 24 equals a 0 where the a was, plus a b times a 4. So I seem to get negative 16 equals b times 4. I think we get that b is also negative 4. All right, so after all that, what's going to happen is that we now, so again, notice that this is not calculus, right? So now my integral is going to be a negative 2, and then I get a, which was negative 4 over this x minus 1, plus b, which was also a negative 4 over an x minus 5 with respect to x. This guy just integrates to a negative 2x. This is technically u sub, but again, since your du is just dx, it's basically just going to integrate the way it looks. So I get a minus 4 natural log of the absolute value of x minus 1. The same thing's going to happen here. This is a minus 4 natural log of the absolute value of x minus 5 plus c. So that answer's not wrong, although it's a little bit squished, right? The other way you're going to see that is with the logs probably combined, right? So you might see something like this. You might see the 4 factored out. If you factor the 4 out, this is the natural log of the absolute value of this thing times this thing, right? Because if you factor out the negative 4, they'd both be on top. Plus c, that's one way you might see it. There are other options, right? There's a ton of different ways this could be written. You could see this with the negative 2x And then if you want, you could put that -4 power on, so you could see that this is a plus the natural log of 1 over, and these guys could both be on the bottom. That's also fine. I mean, I could do this all day where I just come up with slightly different variations of the same answer. Again, it's not your job to come up with all of these answers. It's your job to match them in case you're doing a multiple choice problem. All right. So for P3, same situation. This is improper, so you're going to have to go and clean that up first, right? So first and foremost, you have to deal with that long division. Again, it is worth doing long division if you have a nonlinear divisor, even though there is a caveat that there is a way to make synthetic division work. I'm going to argue it's not awesome, and it's certainly not intuitive. So to get an x squared to look like a 2x squared, I'd multiply by 2, and I get 2x squared minus 10x, and then I'm going to subtract straight down. Well, the 2x squared minus 2x squared is gone. 9x minus a negative 10x is just going to be an x and then a minus 10. This is going to be my remainder. So what happens is this is going to be a 2 plus my remainder over my divisor. So this piece is just going to integrate, right? So the 2 is just going to integrate fine, right? We just have to remember it's there. So this is going to just integrate. And this is going to require a partial fractions decomposition. So what's going to happen is I'm going to get that x minus 10 over this x times x minus 5 should be an a over x plus b over x minus 5. Both of those fractions are missing the other factors. So a is missing the x minus 5 and b is missing the x. When I do my clever substitution, we'll start with x is 0. I get negative 10 equals a times negative 5, so a must be a 2. When I plug in x equals 5, that'll knock out the a term. I get negative 5 equals b times 5, so I get that b is a negative 1. So once we have all that, we get that this is the integral of 2 plus a 2 over x plus a negative 1 over an x minus 5. With respect to x, let's double check that those numbers are right. Yep, that seems to pan out. So again, I'm just going to integrate this as a 2x. I'm just going to integrate this as a 2 natural log of x, no u sub. This one's technically u sub, but again, because your du is just dx, it's really going to look just like regular natural log. When you integrate, it's just got an x minus 5. This answer is absolutely fine. The other way you might see that answer is with this x minus 5 inside the natural log on the bottom. So you might see this as 2x plus a natural log of the absolute value of x squared over x minus 5 on the bottom because it had the minus, and that's also an equivalent answer. Again, you don't have to have all the equivalent answers, you just need to be aware that there's no way to find equivalent answers. All right, so this is getting slightly uglier, right? Again, you should always do a quick check that if you make u the denominator, du is not the top, but it's not. If you differentiate the x cubed minus x squared plus 4x minus 4, you don't get the numerator at all. You don't get any multiple of the numerator. So I'm going to go ahead and try and factor this. So when I go to factor the denominator, right, I notice that this denominator factors by grouping, right? If I group the first two together, I'm able to pull out an x squared, and what's left seems to be an x minus 1. And if I group the last two together, I can pull out a plus 4, and what's left seems to be an x minus 1. So this factors into an x minus 1 times an x squared plus 4. So this is my first instance where I have both a linear and a quadratic factor. So this x squared, rather, plus 3x plus 1 over an x minus 1 times an x squared plus 4 is going to look like a constant over the x minus 1 plus a linear term, bx plus c, over the quadratic. When I go to get my common denominator, it's basically going to be that same situation where I'm multiplying each fraction by the factor it's missing. So a is going to be multiplied by an x squared plus 4, and then the whole quantity bx plus c is going to be multiplied by an x minus 1. Now, clever substitution is tricky here because there's nothing you can do to knock out an x squared plus 4 that involves a real number. The only thing that would knock out an x squared plus 4 is either a plus or minus I, which frankly we just don't want to deal with, so we're not gonna. So I can do some things with clever sub. I could use x equals 0 to knock out b only, and I could use x equals 1 to knock out both b and c. So I'm going to go ahead and use x equals 1 to knock out b and c. That'll allow me to find a pretty quickly. So I get 1 plus 3 plus 1 on the left-hand side. On the other side, I get a times a 5 and then a bunch of 0 because the x minus 1 would knock all that out. So I get 5 equals a times 5. Well, that's nice. I know a is 1. Now I no longer have to stress about knocking out a. Because now that I know what a is, I can go ahead and just knock out b. That'll let me find c because I know a. So I'm going to get 1 on this side because it's 0 plus 0 plus 1. On the other side, I know a is a 1 now, times 4, plus, since I plugged in 0, I'm going to get 0 plus c times a negative 1. So I get 1 equals 4 minus c. Negative 3 is my negative c, so I'm able to get that c is 3. Now that I know a and c, I can find b using any easy x. It doesn't matter which x you pick. I really don't care. I'm going to pick any other easy x. Right? So in my case, I'm going to go ahead and pick x as 2 because I think I'd rather pick a 2 than a negative 1. That's up to you in terms of your style preference. So that's going to give me 4 plus 6 plus 1 on this side. On the other side, I'm going to get a, which was a 1, times 4 plus 4, which is 8, right? Plus, I don't know what b is, right? So I'm going to get 2x, because, sorry, 2b, not 2x, 2b, come on, brain. So 2b, because I plugged in 2 for x, plus c, which was a 3, times a 1. So I clean this up, I get an 11 equals 8 plus 2b plus 3. So I'm pretty sure when I subtract the 8 and the 3 over, I get 0 equals 2b, so I just get 0 equals b. Cool. So after all that work, we still haven't done any calculus. So I got 1, 0, and 3. So when we come back up here, 1, 0, and 3 means that this splits up into a 1 plus 0x plus 3 over this thing. Well, since there's no x at all, this is an arctan. So this is going to integrate to the natural log of the absolute value of x minus 1. But this is my u squared plus a squared, and this is my du. So this thing is actually a 3 times, and if you want, you can switch the order of the a squared and the u squared if it makes you feel better, because that's the pattern you know. So this is actually a 3 over a, right? In this case, a is 2, right? So this is a 3 times 1 over a arctan of u over a plus c. Sorry, my plus c kind of disappeared. So if I clean this up a little, I get natural log of x minus 1 minus a 3 halves arctan of x over 2 plus c, which is kind of intense, right? So there's a lot to it. All right, let's get to the fourth one. So when I factor this one, I notice that I'm going to get an x times an x squared plus 1. So this is the same situation, just a lot easier than the last one we did in terms of the factoring at least. So for the partial fractions decomposition, I know that I have a 3x squared plus 5x plus 3 on top of an x times an x squared plus 1. So that's going to be a linear factor, so that gets a constant numerator, and then a quadratic factor, so that's going to get the bx plus c. When I get my common denominator, it's going to be fairly straightforward. The a is missing the x squared plus 1, and then the bx plus c whole quantity is missing an x. So this time it's going to be a little less advantageous for me to do clever sub, and here's why. The clever sub of 0 would knock out both of these, which doesn't help me all that much. So I'm going to suggest a different option here. So rather than do clever sub, I'm going to suggest that you go ahead and distribute your right-hand side and see what happens. So this is just another way that you can do this. So ax squared plus a plus bx squared plus cx. So here's a kind of cool trick. Because this has to be true for all x, I can say that the stuff on the left-hand side has to equal the stuff on the right-hand side. Since it's true for all x, all the x squared terms have to be equal, all the x terms have to be equal, and all the numerical terms have to be equal. So on the left-hand side, my x squared is just a 3. On the right-hand side, my x squared is a plus b. On the left-hand side, my x term is a 5. On the right-hand side, the only term that only has an x is c. So now I know c is 5. On the left-hand side, the only constant term is a 3. On the right-hand side, the only constant is an a, so I now know a is 3, right? So, and once I know a is 3, I can say, oh, cool, that means that b has to be 0, right? Because 3 equals 3 plus b is 0, all right? So if we go back up, and again, this was technically no calculus, which is one of the reasons that calculus is such a hard class. It's very cumulative. So we got 305, yeah, 305. So we get that this is the integral of 3 over x plus 0x plus 5 over this x squared plus 1. Well, since there's no x term, this is another arctan, right? So what's going to happen is here my u is x, and here my a is 1, because that's my a squared, right? So I'm going to get that this is a 3 times the natural log of the absolute value of x, plus there's a 5 on top of this arctan, right? So this is a 5 over a arctan of u over a plus c. So I'm going to get that this is 3 natural log of the absolute value of x plus 5 arctan of x plus a c. So again, one of the reasons it's really important to put the time in to make sure you can factor and do u sub and that you've memorized all the antiderivative rules is that these problems are a lot of steps. All right, so we have a 5 and a 6 still to go. So, all right, now this one's factored for us, which is nice. Given that it's already factored, that's a solid hint that it's going to be partial fractions decomposition, but it might mean that the problem gets more difficult somewhere else later, because if they did you the solid of already factoring, it might mean they did it because something else more complicated is coming. I always like my linear factor to be at the front, so I'm going to reverse the order. I have no good reason for that. I just always like to make my linear factor the first one and my quadratic the second. So just like we've seen before, right, when I get my common denominator, the a is going to be missing the x squared plus 1, and the entire bx, not squared, my bad, bx plus c, don't know why I made it squared, plus c is missing the x minus 1. So clever sub will help me here, because if I use 1, it'll let me find a. So if I do x equals 1, it's going to knock out this entire back thing, and I'll find a. So I get negative 2 plus 4 equals a times 1 plus 1. 2 equals 2a, cool, a is 1. Great. Now that I know a, I can go ahead and knock out b, and that'll allow me to find c. So I'm going to get 4 equals 1 times 1, plus when I knock out the b, I get c times a negative 1. I get 4 equals 1 minus c, positive 3 equals negative c. I was going to skip you to negative 3. So negative 3 equals c. Cool. So now I know a and c, and then it's a pretty simple matter to find b using either of those. I'm going to pick the easiest x, which in my opinion, the easiest x I haven't picked yet is 2. You could also do negative 1. I just think 2 is easier. So if I pick 2, I get negative 4 plus 4 on this side. On the other side, I'm going to get a times 5 plus, so b times 2 minus 3 times a 1. So I get 0 equals 5 plus 2b minus 3. So I get negative 2 equals 2b, and I get a b as a negative 1. So this is definitely slightly harder, because this is the first time my b hasn't been 0. So this is going to split up into a, which was 1 over x minus 1. That's easy. That'll be a simple natural log. But here's where things get a little trickier. Bx, so negative x plus c, which is a negative 3 over the x squared plus 1 dx. I need to split this into 2 fractions. So I need to split into 2 pieces. I don't have to do this with a decomposition, because the way fractions work is if you have 2 different things in your numerator, you can split them both up over your denominator. So let's go ahead and I'm going to take a quick screenshot of this so that I don't have to recopy it, because that seems to be like a lot of extra effort. Okay, so let's scroll down for a sec. All right, so there's where we're at, and I'm going to go ahead and box off my work that is not calc, right? None of this was calculus, right? So we jump down here, come all the way down to the bottom, and say, cool, this is this. Awesome. So I'm going to rewrite this as 2 separate fractions, as the negative x on top of the x squared plus 1, which will be u sub, and as the negative 3 on top of x squared plus 1, which will be an arctan. So I'm going to end up with 3 pieces to this integral. Right, so in this arctan, my u is x and my a is 1, which also makes my du dx. For this one, my u would be x squared plus 1. My du is going to be a 2x dx, which means du over a 2x is my dx. So what's going to happen is this piece is going to be the natural log of the absolute value of x minus 1. This piece is going to have a negative 1/2 in front of it, and then it's just going to be essentially a natural log. So this is going to be a negative 1/2, the natural log of the absolute value of x squared plus 1. And then this is going to be an arctan, negative 3 over a, arctan, that's not how you spell arctan, of u over a plus c. So I get this. If this were on the AP, you would probably see it without the absolute value on this term because x squared plus 1 is always positive, so you don't need the absolute value. But it's not wrong to write it. I just want you to be aware that if you saw that disappear in a multiple choice answer, it's not wrong. It's just a tricky little thing. And you could combine the logs, but I think that was already a long enough problem without us adding extra to it. So I would say this is about as hard as a partial fractions integration problem gets. To have to do all of that decomposition, and then in addition to all of that, to have to separate the last 2 fractions is pretty hard. So same trick, right? If they do you the solid of giving you the factored form, it's probably going to be ugly for other reasons, as we saw in the last example. So I know that I have a 10. I really like the x minus 1 at the front. I can't give you a good reason why. So I'm going to put an a over the x minus 1 plus a b over the x squared plus, bx plus c over the x squared plus 9, right? When I get my common denominator, the a is missing the x squared plus 9, right? The bx plus c in its entirety is missing the x minus 1. So when I do my clever substitution of x is 1, that's going to let me find a. I'm going to get 10 equals a times 10 plus a bunch of nothing. So a is 1, so that's great. And if this were multiple choice, that's enough sometimes for you to start to figure out the answer because you now know that this is the first part of the vector, right? So like if you had to, if it's multiple choice, you can start to figure out the first piece. If I plug in x is 0, that's going to knock out b and allow me to find c. So I'm going to get 10 equals a times 9 plus, this is going to be 0 plus c times a negative 1. So 10 equals 9 minus c. 1 equals negative c. c is negative 1. Cool. And then I can pick any easy x. I'm going to argue again that 2 is pretty easy, right? Since I already found the other ones, I can plug in 10 equals 13 times 1, right, because that's a is a 1, right, plus 2b minus 1 times a 1. So I get negative 3 equals 2b minus 1, negative 2 is 2b, negative 1 is my b. So now I know that this is going to be a negative 1 minus 1 all over x squared plus 9. And again, I'm going to have to split this into 2. Right? So I'm going to have to split this into 2, which we're going to do at the bottom again because we ran out of space. It's a huge shock. All right, so let's go ahead and separate this because that's not calc work. So let's screenshot again so that I don't have to rewrite this whole thing. All right. Cool. So if we pick up here, I'm going to recognize that this needs to be split into 1 over x minus 1 plus a negative x over the x squared plus 9. That's going to be u sub, right? And then plus this negative 1 over x squared plus 9, which is going to be an arctan with respect to x. So for the u sub, again, I'm going to get that negative 1/2, right? Because if my u is x squared plus 9, my du is a 2x dx. So you can see that when I do du over 2x dx, I'm going to cancel the x's and get a negative 1/2. So this piece is going to be the natural log of the absolute value of x minus 1. I'm going to get a minus 1/2, and then it's going to be the natural log of the u, which was x squared plus 9, inside an absolute value. We can get rid of that in a sec. And for arctan, my u is just x, which means my du is just dx, but my a is 3, right, because it's 3 squared. So I'm going to get that this is a minus 1 over a, right, arctan of u over a plus c. And that answer is totally fine. You don't need the absolute value on the x squared plus 9 because, again, that's always positive. All right, last examples. Let's do a definite integral. So I would suggest that you completely ignore the definite integral stuff until you have figured out the solution, and then you go back, as I've discussed several times, then you go back and plug it in. You just have to clearly separate your work so that it's very, very obvious that you're not at any point saying the definite and indefinite integrals are equal. So I'm going to go ahead and do the partial fractions decomposition first, right? So I'm going to get that this is a 6x minus 2 over an x plus 3, x minus 2. So that's an a over x plus 3 plus a b over an x minus 2. So when I get a common denominator that is the same as the original denominator, the a was missing the x minus 2 and the b was missing the x plus 3. My clever substitution is going to give me a 12 minus 2 on the left-hand side. The a stuff gets knocked out, and I get b times 5. So I get 10 equals 5b. My b must be 2, right? When I do x equals negative 3, I'm going to get a negative 18 minus 2 on the left-hand side. I'm going to get an a times a negative 5, and then the b stuff gets wiped out. So I'm going to get a negative 20 equals a times negative 5. So I'm pretty sure I get, that's not a b, that's an a. I get a equals 4. So now I keep doing work, right? Because I'm going to go ahead and integrate without those bounds, right? So I had 4 over x plus 3 plus a 2 over x minus 2 with respect to x. When I integrate that, I'm going to get that this is a 4 natural log of the absolute value of x plus 3 plus a 2 natural log of the absolute value of x minus 2. Right? And that's pretty much what I'm going to do. I'm going to go back up and I'm going to take that and I'm going to plug in those values, right? So again, I cheat and do all the work separately. And now I say, cool, that's a 4 natural log of the absolute value of x plus 3 plus a 2 natural log of the absolute value of x minus 2 evaluated from negative 1 to 1. And at no point did I say the indefinite integral was equal to the definite integral. Now I'm just going to plug in my values, right? So when I plug in, this is going to be 4 natural log of 4 plus natural log of a negative 1, but since it's 2 natural log of a negative 1, but that's 2 natural log of 1 because it's in an absolute value. Sorry, that's a 2. It didn't quite come out that way. Minus, when I plug in the negative 1, I'm going to get 4 natural log of 2 plus 2 natural log of a 3, right? Because it would be a negative 3. But it's in an absolute value. So natural log of 1 is 0, so I end up getting that this answer is 4 natural log of 4 minus 4 natural log of 2 minus 2 natural log of 3, and that's about as good as it gets. Now, this is that kind of situation where when you have a definite integral, even though it takes the extra minute, it's not a terrible idea to go ahead and plug it in and see what happens. So again, it's quite possible after doing a lot of these math videos in a very short period of time that I did something stupid. It would not be the first, nor will it be the last time that that happens. But let's go ahead and check it and we can figure out where something went wrong if it did. So 6x minus 2 over x squared plus x minus 6. I quit out of there. I want math 9, right? I'm going to go to vars over to y vars and pick y1, comma, with respect to x, from negative 1 to 1. Right, we're going to get an answer. Okay, so now we're going to type in my answer and see if it pans out. Again, it would not be the first time that something went horribly wrong. In fact, I've been a little bit shocked that it hasn't gone horribly wrong other times. 2 natural log of 3, I believe. Hey, that's exciting. All right, cool. So last one in the video, you're going to go ahead and try the same concept I just did. Again, I would highly recommend that you ignore the bounds and just do the work separately and then regroup at the end with the bounds. So I'm going to go ahead and start with the partial fractions decomposition. I know that 7x minus 4 is on top of what seems to be an x minus 4 and an x plus 2. So I'm going to put the a over the x minus 4 plus the b over the x minus 2. And this is much more akin to the level of a partial fractions problem you might see. It's not short, but it's also not as long as some of the others. So the a was missing the x minus 2. Sorry, wait, I made one of them a minus when it should be a plus. The a was missing the x plus 2, my bad. And the b was missing the x minus 4. So when I do my clever sub, I'm going to go ahead and start with the -2, and I'm going to get -14 minus 4 equals nothing for the a's, and then it's going to be a b times a -6. So -18 is -6b. I get b is 3, right? For x is 4, I'm going to get a 28 minus 4 equals an a times a 6. So I'm going to get that a is 4. So now I know my a and my b, right? So if we go ahead, I know that this thing is actually 4 over x minus 4 plus 3 over x plus 2 with respect to x, and that's going to integrate to a 4 natural log of the absolute value of x minus 4 plus a 3 natural log of the absolute value of x plus 2. And then, there would be a plus c, but we're going to do this with bounds. So let's go ahead and, all right. So we just found that this is going to be 4 natural log of x minus 4 inside the absolute value, right? Plus 3 natural log of an x plus 2 inside the absolute value, right? And we're evaluating from 0 to 3. So when we plug in the 3, we're going to get 4 natural log of -1, but that's a 1 because it's in an absolute value, plus 3 natural log of 5 minus, that was when we plug in 3. Right, when we plug in 0, we're going to get 4 natural log of 4, because again, it's in the absolute value, plus 3 natural log of 2. Natural log of 1 goes away, so I end up getting that this is a 3 natural log of 5 minus 4 natural log of 4 minus 3 natural log of 2. So let's go ahead and see how that panned out, right? So I'm going to go back to my y equals, right? I'm going to change this into a 7x minus 4, and I'm going to change this into an x squared minus a 2 in front of the x minus an 8. Cool. I'm going to quit out. I'm going to hit second enter a couple times because I'm kind of lazy. And then I need to change my bounds from 0 to 0 and 3 and hit enter. So we get an answer. Then we're going to check and see. And again, I will be sort of shocked if none of these have gone wrong, because I'm sure I added wrong somewhere and did something silly. Minus 3 natural log of, that was a 2. All right. Hey, woohoo! All right, and that's the end of this video.